Okay, these are the additional practice problems for Chemistry Chapter 2. So question number 1 tells us that a chemist burns 15.4 kilograms of wood and he collects everything that is produced by the fire. And he measures that there are 925 grams of ash. Okay, so right away you should recognize that that unit grams is not consistent with the kilograms that we started with. So the first thing I'm going to do is I'm going to go ahead and convert those grams to kilograms by dividing by 1,000. So it's going to be 0.925 kilograms of ash. And then the carbon dioxide is 15.14 kilograms. So this is CO2, carbon dioxide. And water is 3.12 kilograms. Okay, so this is water, H2O. So in order to burn wood, you have to add oxygen to it. Burning takes place only in the place of oxygen. So this reaction would actually be the wood, this is the wood, plus the oxygen is the mass that we are conserving due to the law of conservation of mass. So if we add these three numbers together, we get that the mass is 19.185 kilograms. And we can go out to, because we're adding, we will go out to the hundredths place. So it would be 19.19 kilograms is the mass of the ash, the carbon dioxide, and the water. And yet the mass of the wood was only 15.4 kilograms. So that means the rest of it must have been the oxygen that we started with. So this is what we end up with. And this is what we end up with. And what we started with would be the mass of the wood plus the mass of the oxygen. So if we end up with this and the wood was this, then we know that the difference is going to be the mass of the oxygen. So this minus this will give us the mass of the oxygen, which is 3.8 kilograms. And we take our significant figures out to the tenths place because we're subtracting here, and the mass of the wood is out to the tenths place. So the answer is that the oxygen would have been 3.8 kilograms. Okay, number 2. 12 grams of carbon react with 4 grams of hydrogen to get natural gas. So 12 grams of carbon and 4.00 grams of hydrogen make natural gas. And there is nothing left over, so that tells us that it should make 16.0 grams of natural gas. And I took this out to the tenths place because this only goes out to the tenths place, and we are adding these together there. So if instead of making 16 grams of natural gas, you want to make 100 grams, how much carbon and how much hydrogen would you need? Okay, so we want to make 100.0 grams instead of 16.0 grams. So how many more times is how many times do we need to up our recipe, as it were, in order to get in order to make 100 grams instead of 16 grams? So if we divide the 100 by the 16, we get 6.25, which again, we're going to go out to the tens place because we're dividing here. So we will take the 6.25 because there's 3 significant figures here. So making 100 grams is 6.25 times as much as making 16 grams. So that just simply means that for the carbon, we're going to multiply times 6.25. We need 6.25 times as much. And the same thing is for the hydrogen. So for carbon, you are going to have 75 grams. I guess 75.0 grams. And for the oxygen, 4.00 grams times 6.25, 3 significant figures would give us 25.0 grams. So if we add those two together, we should get the 100 grams that was desired. Okay, so you would need to mix 75 grams of carbon and 25 grams of hydrogen to make 100 grams instead of 16 grams of the natural gas. Okay, number 3, a chemist decomposes 30 grams of a purple powder. Okay, so we start with 30 grams of a purple powder. And that gets decomposed into 13.6 grams of cobalt. And it says an unmeasured amount of chlorine gas. Okay, so chlorine, how much chlorine? Well, again, we know that because of the law of conservation of mass, that these two compounds have to add up to the 30 grams of purple powder. So 13.6 plus 16.4 grams of the chlorine will add up to our 30 grams of purple powder. Okay, so that's the first part of the question. And then it says that the chemist wants to make 1.00 kilograms of this purple powder. Okay, so this is our recipe to make 30 grams. What would our recipe be to make 1 kilogram? Okay, so first of all, you need to realize that this kilograms needs to be converted to grams. We had 3 significant figures. So I guess we'd have to do this times 10 cubed grams. And we're going to divide by 30.0 grams. So grams are going to cancel. And this divided by that with 3 significant figures is 33.3. So 1 kilogram is 33.3 times as much as 30 grams. So we would need to multiply our cobalt by 33.3. We need 33.3 times as much. And if we do that, we will get, with 3 significant figures, you're going to get 453 grams of cobalt. And we'll multiply the chlorine times 33.3, and that will give us 546 grams of chlorine. If we add these together, we get 999, and that's close enough. Our significant figures is going to keep us from reporting exactly 1 kilogram, but it would be 999 grams. So you need to have 453 grams of cobalt and 546 grams of chlorine to get the 999 grams, or 1,000 grams as it were. Okay, number 4. A compound is decomposed into its constituent elements of carbon, nitrogen, and hydrogen. When it is decomposed, the problem tells us, you end up with 12.0 grams of carbon, 14.0 grams of nitrogen, and 3.0 grams of hydrogen. So then the problem asks us, what was the mass of the compound before it was decomposed? The law of conservation of mass says that mass cannot be lost. So the sum of these 3 would need to be the mass that we started with. And we're adding here. So it's going to be 29. We're going to report out to the 10th place because that is what each of these is reported out to the 10th place. So 29.0 grams of the compound is what we started with in order for it to decompose into those 3 elements. Okay, number 5. In an experiment to make hydrogen peroxide, a chemist, so we're going to make hydrogen peroxide, and to do that, we are going to mix 20.0 grams of hydrogen and 20 grams of oxygen. Okay, so that's what gets mixed together. But we find that only 21.3 grams of hydrogen peroxide is produced. And then you have some leftover hydrogen. Okay, so it doesn't tell us that any oxygen is left over, so we assume that all the oxygen was used up. So we used 20 grams of oxygen. So then how much hydrogen should we have used in order to get the 21.3 grams of hydrogen peroxide? Again, law of conservation of mass. If we end up with 21.3 grams, that means that we only, to make 21.3 grams, only required the amount of oxygen and hydrogen that was used needs to add up to 21.3. So since we had no oxygen left over, we know that all of it got used, and therefore the amount of hydrogen that was used would be just 1.3 grams to get our 21.3 grams of hydrogen peroxide and have nothing left over. Okay, moving on to number 6. So number 6 tells us that we are going to make 152.5 grams of calcium nitride. And to do that, we use 100 grams of calcium, or mix 100 grams of calcium and 100 grams of nitrogen. However, we are told that we have leftover nitrogen. So we end up with 152 grams of calcium nitride, but leftover nitrogen. Okay, so if we mix together 100 grams of calcium and 100 grams of nitrogen, and yet only end up with 152.5 grams of calcium nitride, because of the law of conservation of mass, to end up with this amount of calcium nitride, we would have needed only 52.5 grams of nitrogen. Okay, so that's our recipe to get the 152.5 grams of calcium nitride. Okay, so then the second part, the question that we are asked is, if you wanted to make 1 kilogram of calcium nitride, how much calcium and nitrogen would you use? Okay, so again, this is, so we want to make 1 kilogram. Instead of making 152.5 grams, we want to make 1 kilogram. And that is the same as 1.0 times 10 squared, 10 cubed. Grams. And instead of making 152.5 grams, we want to make 1,000. Okay, so the grams will cancel, and what we get for our conversion factor then, with 2 significant figures, is 6.4 times. Okay, so making a kilogram is 6.4 times as much as making 156.2. So that means that each of our elements needs to be multiplied times 6.4 to get the amount that would give us 1,000 grams. I'm sorry, this might be 6.6. This might be 6.6. Let me check my math on that. Yeah, so that's going to, with two significant figures, that would be 6.6 times. 6.6, 6.6. So this would be 660 grams of calcium, and 52.5 times 6.6, it would be 350 grams with just two significant figures, 350 grams. And again, this is not going to come out exactly, but it'll be close to the 1,000 grams that we want. And the answers are just going to be different based on significant figures. Okay, so you would need 660 grams of calcium and 350 grams of nitrogen to make 1 kilogram of the calcium nitride. Okay, number 7. Okay, so number 7 says that we're going to make calcium chloride. So 100.0 grams of calcium plus 100 grams of chlorine are mixed together, and we end up with 156.5 grams of calcium chloride plus leftover calcium. So that means that we really only, to get this recipe, what we needed was 56.5 grams of calcium. How much chlorine and calcium should be added together in order to get 1.00 grams, or 1.000 kilograms? So 1.000 kilograms times 1,000 milligrams per kilogram. So that is 1,000 milligrams of calcium chloride is what we want to make. So 1,000, I'm sorry, this should be grams, not milligrams, grams. So 1,000 grams divided by 156.5 grams will give us a factor of 6.39. And technically we need to, with 4 significant figures, so this would be 1.000 times 10 cubed grams. So in any case, we have 4 significant figures. So 1,000 divided by 156 6.390 if you round up. So it's going to be 6.3897. And we can have 4 significant figures, so we would have to go 6.390 times. So making a kilogram is 6.3 times as much as making 156.5 grams. So each of our components then needs to be added, needs to be multiplied by 6.390. So this, with 3 significant figures, this would be 361 grams of calcium. And it would be 639 grams of chlorine. And if you add those together, you're going to get 1,000. 1,000 grams, which is what we wanted to be able to make. We want to make 1 kilogram, which is 1,000 grams. Okay, number 8. A chemist adds 50 grams of nitrogen to 50 grams of hydrogen and ends up making 60.7 grams of ammonia and some leftover hydrogen. Okay, so we start with 60.0 of nitrogen. And to that we add 50.0 grams of hydrogen. And you end up with 60.7 grams of ammonia plus leftover hydrogen. So that means we didn't use up all the hydrogen. So that means all the nitrogen was used up. So what we really used for the hydrogen would have been 10.7 to get the 60.7. Okay, so now what, instead of making 60.7 grams of ammonia, what if you wanted to make 100.0 grams of ammonia? So 100.0 grams of ammonia divided by 60.7 grams of ammonia. The grams are going to cancel, and your ratio is, with 3 significant figures, is 1.65. So you have to make 1.65 times as much if you want to make 100 grams compared to 60.7. So that means that each of our ingredients, we need 1.65 times as much. So nitrogen times 1.65 and hydrogen times 1.65. So the nitrogen comes out to be 82.5 grams and the hydrogen ends up being 17.7 grams. And that 10.7 times 1.65, 17.7 with 3 significant figures. So adding those together, you'll get 100.2. And we were shooting for 100, so that's close enough because of significant figures. So to get 100 grams of ammonia, you would need to add 82.5 grams of nitrogen, and you would need 17.7 grams of hydrogen. Okay, number 9. Number 9 says we are going to react 12 grams of carbon plus 4 grams of hydrogen. And that will make methane, which is a gas, and there will be, it tells us there's nothing left over. So that means that our total methane, because of the law of conservation of mass, had to be 16 grams. Okay, so then it says, what if you react 50 grams of carbon with 50 grams of hydrogen? How many grams of which element will be left over after the methane is made? Okay, so for this one, what we're really looking at is we're looking at the ratio between the carbon and the hydrogen. So this tells us, if we look at, for every 12 grams of carbon, to get methane, we need 4 grams of hydrogen. So in other words, the carbon to hydrogen ratio is equal to 3. Okay, so for every carbon, for every hydrogen, there are 3 carbons. Okay, so it's 3 to 1. 3 carbons for every 1 hydrogen. So if we wanted to make if we mix together 50 grams of carbon and 50 grams of hydrogen. Okay, so 50 grams of carbon and 50 grams of hydrogen. Okay, so this tells us that we need the carbon to the hydrogen has to be there has to be 3 carbons for every hydrogen. So that means that the one that's going to be left over is the hydrogen, because this recipe calls for less hydrogen than it does carbon. So if we use 50 grams of carbon, then what number is a third of 50? So 50 divided by 3 is 16.7 grams of hydrogen is what we would need. So this would make methane if you mix 50 carbons and 16.7 grams of hydrogen. So if we started with 50 grams of hydrogen, then what would be left over would be the difference. So 50 minus 16.7. So you would have 33.3 grams of hydrogen left over. Okay, number 10, we are going to make aluminum sulfide. So we mix 54.0 grams of aluminum and 100 grams of sulfur. And we end up with 150.3 grams of aluminum sulfide and some leftover sulfur. So we didn't need all that sulfur. So how much sulfur did we need? Well, what we needed was the 150 minus 54. 150.3 minus 54. So really, of the sulfur, we really just needed 96.3 grams. Okay, to get to, because now we wouldn't have any left over, any of the sulfur left over. How much aluminum and sulfur if you wanted to make 100 grams? Okay, so this one's a little bit different because we now we want to make 100 grams instead of 153. So 100 is a smaller quantity than 153, so our ratio is going to be less than 1. So the ratio that we get is going to be with 4 significant figures, it's going to be 0.6653. Okay, the grams cancel, and we're just left with that as a ratio. So then we want to make 100 grams of aluminum sulfide, we would need to multiply this times our multiplying factor, 6653, and that would give us 35.93, well actually with 3 significant figures, 35.9 grams of aluminum, and then 96.3 grams of sulfur times our multiplying. Will give us 64.1 grams of sulfur. And if we add those two together, we're going to get 100.0 grams of aluminum sulfide. So one way for you to check to make sure that your answer is correct is that the components that are being mixed together should add up to the quantity of the compound that you're trying to get. So you're trying to get 100, and these add up to, these two add up to 100. That tells us that we got the right answer. Okay, number 12. These problems now are starting to get to be a little bit repetitive, but this one is a little bit different. So number 11 says that a student does a chemical reaction with two chemicals, and the total mass of the two chemicals so we're going to mix these two chemicals together, and the mass of the two chemicals is 17.0 grams. When she is done, the student finds that the mass of the chemicals that she collected is 17.8 grams. The teacher says the student obviously contaminated the experiment with something else. So something was in there besides these two chemicals. How does the teacher know this? And what is the mass of the contaminant? Okay, so the teacher knows it because the law of mass conservation says if you start with a mass of this amount, that's the mass that you're going to end up with. You can't end up with a larger mass than what you started with. So then what was the contaminant? Well, the contaminant would be the difference between these two. So 0.8 grams is what the mass of the contaminant is. Okay, number 12 has four parts, I guess. So this one is a little more complicated, so we'll take it step by step. So this says that a chemist is going to mix 63.55 grams of copper with 100 grams of chlorine and ends up with 134.5 grams of light blue powder plus leftover chlorine. Okay, so right away that tells you that the chemist used too much chlorine. If you had leftover, then some of that chlorine was wasted. So that means we used all the copper and some of the chlorine. So how much of the chlorine did we use if we made 134.5? Well, it's just going to be 134.5 minus the 63.55 grams of copper. We know we used all of that. So in order to get this amount, we really only needed 70.95 grams of chlorine. Okay, so now part A says how many grams of copper and chlorine would be needed to make 500 grams of a light blue powder and have no leftover chlorine. Okay, so we want to make 500 grams, but the recipe that we have is for making 134.5 grams. So how many more times is 500 than 134.5? And the answer is 3.7. We have four significant figures, so 3.717 times. Okay, so that means that to make 500 grams, our recipe is for 134 grams. So we'll multiply that times 3.717 for the copper. And we will do the same thing, the 70.95 grams of chlorine times 3.717. So if we do this multiplication, 63.55 times 3.717, you would need 236.2 grams of copper, 236.2 grams of copper, and 70.95 times 3.717, 263.7 grams of chlorine. Okay, and we check these because they should, I did something wrong there. Oh no, it was 500. So these two should add up to what we were trying to make, which was 500. And that's going to come out to 499.9. That's close enough. Okay. So to make 500 grams of the light blue powder, we would need this much copper and this much chlorine. Okay, so that was part A. Let's move on to part B then. Okay, so part B says that another chemist combines 100 grams of copper and 111.57 grams of chlorine. And it makes a powder, a solid, and nothing is left over. Okay, so then we are asked, is this compound the same as the compound that we made up here? Okay, so here we need to look at the ratios between the copper and the chlorine. Okay, so what is the copper to chlorine ratio? Copper divided by chlorine. So up here we had 63.55 grams of copper, and we had 70.95 grams of chlorine. So what's that ratio? 63.55 divided by 70.95 equals 0.8957. So that just means there's, for every chloride, there is 0.8957 coppers. Okay, so there's less copper than chlorine. And then what is the ratio down here? But copper divided by chlorine, 100 divided by 111.57. Okay, grams cancel, you're just left with a ratio. And there we get 0.8962. So these numbers are close, and so we would conclude that they are indeed the same blue powder. We're comparing this number to this number. Okay, so they are the same powder. Okay, so that was part B. Then part C says that another chemist mixes 63, this is C now, 63.55 grams of copper with 35.45 grams of chlorine, and there's nothing left over. Is this the same compound as A up here? So now, again, we're going to look at the ratio between copper and chlorine. So copper, we're going to take 63.55 grams divided by the chlorine, 35.45 grams, and 63.55 divided by 35.45. The ratio is 1.79. Okay, so that is quite a bit different than this one. So that tells us that the powder that was made in part C is not the same. Okay, then part 12D. Okay, so part D. If the compound made in A is composed of 2 chlorine atoms, how many chlorine atoms are made in part C? Okay, so we need to go back and look. So in A, the ratio in A, ratio of carbon to chlorine. So for every carbon, or for every copper, sorry, for every copper to chlorine ratio was 0.8963. Okay, and that tells us that there, in terms of atoms, that's 1 copper and 2 chlorines. Okay, and then D, the ratio that we got for D was 1.793. So copper I'm sorry, it was C. So copper to chlorine was 1.793. So if this is 1 copper for every 2 chlorines, then this would mean that there's less copper for each chlorine. I'm sorry, there's more chlorine for each copper. So this would be this times this. it would be 1 copper for each 1 chlorine. So I guess what we need to do is go up to, let's see, let's go back here and let me write down I shouldn't have erased this, but let me go for part C. What we found, let's write down what we found so part C was 63.55 grams of copper and 35.45 Okay, so let's go. Part C was 63.55 grams of copper for 35.45 grams of chlorine. Okay, so that was C, and for what we got for A was 63.55 grams of copper for each 70.90 grams of chlorine. Okay, so we were told that this is 1 copper for every 2 chlorines. 1 copper, 2 chlorines. So what would the ratio between copper and chlorine here be? So both the coppers are the same, right? So that's going to be 1 copper. That'll represent our 1 copper. So when we look at the difference between the chlorines here. So this chlorine is half as much as this one. So if this is 2, then up here would be 1. Half as much as that one because the number of grams is half as much as that. Okay, so that is number 12. And then the last one that we will do is number 13. So in number 13, a chemist is making 2 different compounds from nitrogen and oxygen. So in the first one, there's 14.1 grams of nitrogen, and there are 16 grams of oxygen. And that makes 30.01 grams of a gas. Okay, so that's the first one. And there's nothing left over. Okay, the second one, you mix 14.0 grams of nitrogen. And you mix, okay, well actually it tells us, suppose you, and then it's not going to tell us how much oxygen. We're going to figure that out. How much oxygen do you need? Okay, so this tells us that for the first gas, it's 1 nitrogen for each 1 oxygen. Okay, so they are in a 1-to-1 ratio. So that would be like NO. Okay, 1 nitrogen and 1 oxygen. But then the second one, they say that there's going to be, for each 1 nitrogen, there are going to be 3 oxygens. Okay, so notice that the amount of nitrogen here is constant. This is 1-to-1 ratio. So if we keep the amount of nitrogen constant, but now we need 3 times as much oxygen. So this would be 16 times 3. So we would need 48, right, 16 times 3. Yes, 48 grams of oxygen to make a gas that was a 1 nitrogen for every 3 oxygen. Okay, so again, the nitrogen is constant. It's the same in both. If this side represents 1-to-1, and this side is supposed to represent 1-to-3, then we would need 3 times as much oxygen for this one compared to this one. Okay, so that is that's it for the problems on the extra practice problem. Let me say, if I will go ahead and answer number 14. It's not really a problem, but it says which of the 2 following atoms would be isotopes. And in order for something to be an isotope, it has to have the same number of protons and different numbers of neutrons. So looking at number 14, A and B both have 11 protons. So that makes them the same element. And then A has 12 neutrons. And B has 11 neutrons. So these A and B would be isotopes of each other because they have the same number of protons. C and D each have 12 protons. But they also have the same number of neutrons. They each have 12 neutrons. Okay, so they are not isotopes of each other. In fact, they are the same. So they're not, they would be the same element because they have the same number of protons, but they're not isotopes because they have the same number of neutrons. And isotopes have the same number of protons, but different numbers of neutrons. Okay, that is it for the additional practice problems for Chapter 2.